Today we want to speak about 3D reconstructions more. Anchi Cheng starts with LATLINE details, what this is and how to fit them. I will then present some 3D merging, and Cheng will tell us more about the single particle approach in 3D. Yeah, so Anchi, please.
Okay, today I'm going to tell you about lattice line fitting. This is the step where we apply a model fitting to the special form of Fourier transform that we get in 2D crystal. The program that's in MRC to do this is called the LATLINEK, stand for 2000, K I get 2000, and the special form for it. Then it was written by David Agar while he was in MRC in 1983. And it's a very good program, complicated inside, in terms of how it does fitting, how to get the function over. But 2DX will help you to set up the parameters, so it's not as bad. Now first, Henning already told you about the lattice line. It came from the fact that if, instead of a repeating unit, so that's in 3 dimensions, in all 3 dimensions, where you will get discrete spots in a Fourier space, because we don't have a repeating in the 3rd direction, in the z direction. So instead of discrete points, like what we get in xy direction, in the z star or z star direction, it's actually a continuous line, just like what you would get from a single particle. So that's represented here. In the 3rd dimension, if we consider the original form of the function is a sinusoidal form with a period of a, and if you apply an envelope to it, so that restricted to just one of those, then that's what we get in a lattice form, lattice line. Normally, when you see this, it's going to be represented in a complex form as a vector with amplitude and phase. So that's usually you have amplitude and then shown as phase. Okay, the whole idea of doing a lattice line fitting is no different from what you do a polynomial fitting of any data that you get normally. So I'm hoping that you learn somewhere about the fitting. May not know exactly how it works, but you know what you need to think about it. So let's say I gathered some data for my measurement, biochemistry or physics, whatever. I will have points at different places in space. So you will have, if you look at the x and the y, then here are your data points. They're never, almost never sampled regularly. So that's not what you really want. If you want to know a specific value as somewhere in x, you want to know what that y value is. That's why we do fitting on this, to describe it and being able to estimate the y value at that point. So what would you do? Okay, number one is you have to define the model. So for example, in here, I look at this data, I say, that looks like I can fit, I probably cannot fit a straight line over it. So I'm going to use 2nd order polynomial. So I will need 3 parameters to determine this model. So I know this is the shape if in its general form. Second thing you would do is do some sort of least squares fitting. If it's a polynomial, you usually can use what they call the linear least square fitting. If it's some function that's more complicated, then you have to do a nonlinear method. Most of the time, the nonlinear linear methods are harder to apply, so you tend to have to do a guess at the beginning. And then there are algorithms, and you'll find that in books like Numerical Recipe or to apply that. So you need to do that. First, you need to have a guess. And then you use one of those methods to calculate, and you take your function, you use those guess values for your parameters that you try to fit. Then you'll be able to go for any x value, then you'll be able to get the value that according to the value of y according to your guess and your model. Then you will be able to compare your actual data with that value of from your start off from your guess parameters. Now you have those, then you compare them, you take the differences, then you say, okay, I'm going to find out how far off I am. Then you end up with some sort of a residual numbers. You do better if you are weighting each of the points according to how accurate you think that number is. Then there are mathematical formulas to give you all those results. So that's what you will do. And then you have that, you have the next guess, then you go all over again. You start with those guess value and then you do the same thing. Okay? So that's how you do the fitting. And most of the time, this is done inside the computer calculated its processor. You don't get to see it. So a lot of the time, there will be the third step. Oh, sorry, I forgot one more. There's one. The third step is, of course, since you want this value at some other sample point. Once you have a good estimate of your parameters, then it's very easy to calculate the value at where you really want to sample. Okay? So that's the general procedure of any kind of fitting. They usually are done this way. The last one is, as I try to get a little too fast over, is the display. And you have to, oftentimes you want to display that to the human being, what the result is. Okay? So that's the 4 things that you do. So in Lattice 9, the original MRC program, so that's divided into these 4 steps. The parameters in there are quite a lot of parameters, but you can separate it out in this 4 steps. The first one is to define the model. There are many parameters here. The most important is the size of your envelope, okay? And how you're going to do your parameter fitting. I'll go through this in more detail later. Second one, it needs to do the guess. So it needs to use the data that's already there to provide the initial guess. This is where you provide it with a bin size so that it can say, take this value, take all the numbers in here to give me a good initial guess of where that is. Then you can use that to be able to give you some the parameter values that you need for your model. Then you plot that using the guess value, and then do the nonlinear least square fitting. So we don't need to know detail how they did it, but you will have data points, and then you will put, you can compare that with your measurement. Then you fix that, then you get the value in there. Okay. And the last part of the parameters is just for sampling the curve. Okay. So everywhere where I put some numbers here, there will be a parameters in that particular program to deal with it. A lot of this you don't have to worry about anymore in 2DX because the sample curve, this is, as I said, optional. It's just for display purpose. Program can easily estimate what would be a good way to make it look easy to read by us. It looks, the curve will look smooth for us. So that can be taken care of. The guess as well, it's pretty easy. In fact, it's pretty easy to estimate what would be a proper bin size. Most of the time, it will be like you would divide, between for about half to 1/3 of that value. Usually, is good enough. You want a bin size that's good enough to have a few data points there, so that it will have value in there. And that can be taken care of. Now, this part If you know the form of the model, the program can take care of that. So you don't have to think about it. And these are little details, the little details of your model. And that usually doesn't create strong effect on your model. So that can be estimated as well. So basically, you just don't want it to be really sharp so that you get aliasing effect in your transformation. So that's usually, doesn't cause that much harm. Okay, so at the end, So at the end, what you left really is defining the model. Okay, the model itself, which is this distance, and then you need to define how you are going to sample at the end, which is defined by this value called a lat. It's going to be your cell parameters in the z direction. If you are looking at a 3D crystal. Okay. So that's really, let me see, 3 values that you need to care of. One here, let's see, if you have a 0, then you have a minimum, you have a maximum, that gives you the distance for your envelope. And then you need this value for defining how you sample. So 3 values you really need to think about. But they are really important values. So now, the values for the Rmin and Rmax determines your envelope function. So I'm going to go into more detail of what it means. I just said at the very beginning that the envelope function is being used to limit your original periodic crystal, you may say. If you think it originally is a crystal being limited by this envelope, you basically do multiply this two, you end up with just what's in the middle, one layer of this molecule. You do a Fourier transform of that. This we've learned that will give you a single frequency. I'm plotting this here, it's the 0, so I'm plotting both in the positive and negative direction. This is just the amplitude, showing the amplitude. And this transform turns out to be a sinc function. Okay, that's centered at 0. And it's there's a distance here. You will always see a node at the distance of 1 over d, which is the size of that envelope. So again, we use the Fourier transform trick. If you multiply in Fourier space, you convolute. If you convolute in real space, then you multiply. So we do the same thing here. Then we end up with what we expect it to be as a lattice line form, like a lattice line. No, the way that we need to express it. Okay, so this two convoluted into that. So it's defined with Rmax and Rmin, not just as a d value, because now if let's say you have something that don't have twofold axis in the z direction, then you don't expect that going from the origin is going to have the same distance to the other. This envelope function obviously have to be about the size of your protein density. Okay, it needs to be able to cover your density well, because that means that if it's too small, then you're cutting off your original periodic thing. It creates extra bits of it. So that's very important to make it to be about the size of what you expect it to be. By defining this, you define the width of this sinc function in the Fourier space. Now say that I have it's this wide, and I make it wider, then what's going to happen is that the sinc function becomes narrower. So you can see the form of the sinc function changes with the width you define. This part is done by the computer, so all you are doing is defining this, and it will make the shape correctly in the Fourier space where you are actually doing the fitting. Now, I can't stress enough about the importance of defining the correct function. If I have fit that example I had with polynomial with straight line, it's not a good fit. I need to use proper number of parameters in there in order to get a reasonable fit, a meaningful fit, I should say, for the data point. So in terms of the LATLINEK 50, that means that you need to choose the correct size of the envelope. So if your protein, if you look at your data, it's scattered like this, you use the correct size of your envelope, then it's going to follow the curve. If you use something that's much smaller, you will find the curve doesn't actually fit your data properly. So it's a way of finding out if you don't know your protein well enough to know how wide it is. You can start off with a guess of what you think it should be. A layer of a membrane protein, probably 100 angstrom or something, sometimes a little smaller. If they are, if it's just single layer, there's no two-fold symmetry in there. But for something like this, when you put it into the program, then it doesn't fit. That usually means that no, there's something that you didn't realize about your protein. It's not the program is going wrong. It's because the value you put in is not realistic for that protein. So you should know how your protein behaves. This particular example is gap junction. The protein I showed last night is extra long, so it definitely would not be able to fit with something that's 100 angstrom. So we need to do something like 250, 560. You can tell from the slope of your data as well. When it's larger, you saw that sinc function has a big slope because it needs to go down to 0 very quickly. So it will have a big slope over here in most places. So that's a telltale sign that you have something that's a lot thicker. Now, of course, people...
You really overestimate what happens.
Yeah, so here is what happens when you overestimate. Okay, so polynomial function, you know that I can keep on adding that. It will still fit at where my data points are. But eventually you get something like this, right? That's wiggling everywhere. It still fits at everywhere you have the data point, but it becomes very meaningless. And also you are not getting, let's say I want to sample it here, away from where my data point is. So it could be a value really high and really, really low. You're not using the power of fitting to create an averaging effect on your data. Okay, so if you fit too far, that means that your data you're going to get, when you start sampling, it becomes noisy. Because you're not using all the neighboring data to create your sample point. That makes sense? So you don't want to make it too big. Okay. So that's that. I will clear on that part because I'm going to move on to something different. Okay. So that's defining the envelope function. Now I'm going to go a little bit on the one theory that's affect how they do this parameter fittings. Okay. There's a theorem called the Whittaker-Shannon sampling theorem. It doesn't work for all the functions, but for the function that we are using, the envelope function, the sinc function, it works. So this is very useful because it makes it easier to do this fitting. What it says is that, let's say I have one of this term, one of this function, one of the sinc function is centered at the z start of 0. I have an amplitude of 570. I have a phase of 0. So it's plot out something like this. Okay. I have another one that at 1 over d. That is centered at 1 over d. And the minus 1 over d. to be symmetrical, and has amplitude and a phase of some other value. So these two each form a curve like this. If we, in a situation where we are doing our fitting, we have both of them present, then you add those two up, you end up with a curve like this. Okay, what this theorem tells you that you are adding these two terms together, but at a certain point, which is z equal to 0, this original position that is being centered at, and this original position that this function is being centered at, those values almost never change. Okay, in other words, I don't have to know that much about every function. I just have to say, okay, if I measure the value at z star equal to 0 to be this value, that must be the amplitude of the term for z is equal to 0. Okay, so you only have to do, instead of having to do parameter at every point, you only need to know this value over here, this value over there, and if you have more terms, the next value on at 2 over d. Okay, so so when you are doing fitting, you don't want that many parameters for you to estimate. The more they are, then the ratio of your data points and your parameters becomes small. It makes the fitting not as good. So you just, because of this theorem, we can minimize it, make it a lot easier. This also means something else in this. First, this is a reducing number of parameters. I already said that. Second is that from here you see that because of the shape of the amplitude of z, there's a slight effect over here, but when I go further and further out, its effect becomes really small. So it's not going to affect your result. It makes the guessing part easier. It doesn't have to do much to guess the first value almost correctly. The third part has to do is because it's damped out really easily. Let's say I have data that fits to high z values. The fitting estimates what's the amplitude and phase at 0, estimates the value at 1 over d, 2 over d, 3 over d, 4 over d. It's really only needing to use the values that's around it to do this fitting. The value over here doesn't affect the value over there. Okay? Which means, let's say you started your fit earlier when you only have low tilt data. So you only have this much of data. Your fitting result is going to be very similar to what you get when you have more tilted data. Okay, so that's not going to affect the value here at all, almost nothing. And it's going to, the high tilt really only give you the extension of this line to the higher z value, z star value. Okay, so if your fitting is not good when you have low tilt, high tilt is not going to help you. So if you don't get the model right, it's not going to change the way it behaves. Okay, so that's that. So the last part is just about evaluate how at the end, when this program runs pretty fast, it gives you plots, gives you statistics. So what you want to look for is that you want to see the general fit. As I said, different slope indicates that you need to use different envelope size in order to get your model right. The second thing is that has to do with what Henning showed yesterday. When you look at the list of the merged data, you have some of them have round defocus at a certain diffraction spot. Then you have phase, some of them are going to get flipped. So 180 degrees is a really big value to be different from the original. So if you do a lattice non-fitting, you're going to see that particular point jump out from everything else. It's going to reduce your phase risk residual, and it make your fitting generally worse. So it is you want to make sure you get if you get the right defocus, you will get a better result. Your tilt geometry being wrong, it will also change the result. So that will affect the z value where your sample point will be placed at. And the third thing is that, are there any missing region? If you don't have data, then you're not going to have parameters to put in there for the fitting. It gives you two main statistics. One is overall weighted R factors. This is calculated purely from amplitude fitting, part of the fitting. The fitting uses both amplitude and phase with some weighting factors. For images, you want to weigh your phases more because we know that's more accurate. If you have diffraction, you probably want to do equal weighting on both of them. And it also gives you overall weighted phase residual. Christina gave a very good example yesterday about that we use the term phase residuals for many different outputs in our processing process. And in here, the phase residual is referring to the deviation from the lattice line, okay, in the phase value. So if you weighted the whole thing together with different lines, you can get an average, and the lower, the better. If you get below 20 degrees, that's really good. That means that you're probably done with your refinement. Okay, so that's the two values here. Let's see. So I seem to be going ahead of myself all the time. So the phase residual is the fitting error. Since we had those questions early on, so I give a slide here. When you do a normal linear fit, from the error of each data point and how far away it's from the line, the parameters that you estimate, you can give a sigma value there. So that's the error of the fitted parameters. Same thing here, when we are doing here. If I'm sampling at the same distance as my envelope, then this error bar that's shown here will be doing the same thing, because as I said, the parameters are the amplitude and the phases at each position of your 1 over d, 2 over d, and 3 over d, etc. So this is the error determined by how well all these points around it is fitting in. Okay, it would be a little different. I look at Fabian's data, and his sampling, what he used as the C values, seem to be a lot larger than the envelope value. That's okay to do, but what you will see is that you have a lot of points where it's sampled will have the equal number of this error in there, because it doesn't actually recalculate the error in between. It just uses the same value within it. So originally it only internally calculated wherever it is from your model. It didn't do it from the way you sample. Okay, so this is what I was saying about using the numbers. It's in practice, it's almost like it's using a number around it to estimate that error. Okay, so summary. We have R min and R max. You're going to have to define in 2dx. That gives you your envelope function that depends on your protein density. It must cover the protein density and about right at the right size. You give a value for A bat, And that's basically your repeating unit in the 3D crystal parameter. And the third thing is that you need to remember to look at the result to help you understand if you get your model correctly or not. So that's all. Questions?
So I think for us it would be great if you could just sit down with us and look at a few projects and
Yeah.
look at how we fit the lattice lines.
Look at a few your project and understand what it's doing. So let's say, for example, I have a data that's really sparsely populated. Then the fitting is not going to be very good. The program tends to, it's going to give you, I think, the error bar would be like 90 degree or more. That's in the case, you know, it really doesn't have a fit, or you have a single point that the error is, you know, is basically the whole thing. And on part of once you have the 2 points in there, then it starts to have an estimate of error. As you know, if you average in two values together, you know, you have a sigma value that doesn't mean a lot. You have 3 points, you have 4 points, 5 points, and the more you have, the sigma value that you get is more meaningful.
So all these parameters exist in 2dx, and I think there are probably 10 people in the world that know how to do that.
But I think I looked at the interface yesterday. It reduces down to what I just said here, and you also added the bin size, and I think the bin size can be taken off as well at this default to some value, because that's only an initial guess. I did a few testing on that. So you change the bin size, it doesn't actually change your data if you have enough data in there to use a smaller bin size. So that can probably estimate it out from your data as well.
Yeah. When you make your first construction, you do it in the P1 symmetry, right? You don't apply symmetry, or do you? Or can you use a symmetry after that to estimate how good the data are?
You can use, let's say you don't know your symmetry, and then you are not sure at all, you want to use P1 to process all the time, then you can look at your lattice line. Now, if you have enough data, the way the data distribute, it's going to help you to find out if you have a symmetry or not. So, for example, I have a P6 symmetry. Then I actually have P6 symmetry, but I process and merge this as P1. So when you get to this step, you do give it what your symmetry is, because when you merge, you gave it symmetry already. So you look at your lattice line, or how your data is populated in the whole z direction. You're going to see inversion around 0. For example, then you're going to see that your phase is on this part of the say go this way, and on the other side of 0 in the minus direction, it goes that way in exactly the same way. So that's an indication that you have a symmetry that you didn't apply in there. So that's one of the things that will help you. Most of the cases, well, you can tell it just when you are doing the O space, which is the symmetry determination, why is it untilted. It gives you a very good idea of whether you have a symmetry or not. And you get that from you just projection that you can see kind of a symmetry in there. If you suspect that's not, let's say you don't know if that's the case. You apply a symmetry that shouldn't be there. Okay? When you get to this point, you have 3D plot of your data point. What you will find is that instead of getting one line, your data is going to aggregate into 2 lines instead of 1, because some of them are supposed to be at a different value from the other. So because when you apply symmetry, you folded this back the negative side, assuming there's that inversion I talk about, put it over here. Now, if it doesn't really have that inversion property, then it's going to end up fall out somewhere else. So you end up with too much. Then that tells you that you apply too much symmetry.
Quick question. You said the bin size.
Yeah.
You talked about the bin size. And I know if I got it correct, so bin size can be defined by A-left, right?
Bin size is determined by the D value.
D value.
Yeah, because this is all fitting. Okay.
Yeah.
The A-lot is really only used in sampling.
Yeah.
So none of this really apply to the A-lot. It's only the fitting.
Actually, I'm not clear. If you merge in P1, but your symmetry is really P6, do you need to remerge again? And would that higher symmetry help your lattice line fitting because there'd be more spots?
Yes. Yes.
So you do need to.
You do need to remerge, because if you merge in P1, you're not going to be at the right origin. Every symmetry, the origin is usually defined at the point where it's the highest symmetry. So for P6, the origin is defined at the 6-fold axis. If this is a P1, it can be anywhere because it doesn't need to do anything. It just needs to make sure it repeats in the same way. So if you have higher symmetry, you need to first merge it to its proper origin. Otherwise, your phase value is still going to look wrong. They can't do that inversion correctly I was talking about. Anything else? All right.
Thanks a lot, Anchi. So the coffee break. We're here at 10:15.